In chapter 12, lesson 4, we talked about events being mutually exclusive or whether or not they had some overlap. Another way that we can talk about an event being mutually exclusive is saying that they are independent. So when we have an independent event or a dependent event, one affects the other one. So in some ways, there's ways that we can think of it at the same time, or there's ways that we can see it as something completely different, okay? So mutually exclusive means there's no way that event can happen. The two different events can happen at the exact same time. Independent can say there's no way they can happen at the same time, and also that subsequent one. So we've got event 1 and then event 2 and event 3. And no matter how far we go down the line, whatever we do from event 2 for event 1 has no effect on event 2. So when we are looking at something when it has no effect on what's happening the next time around, we can call that an independent event. An example of an independent event is that I have a die and I roll the die. And then I roll the die again. Now, it doesn't matter what I got in the first die. I still have the same options the next time around. Or say you and two friends walk into an ice cream shop. And you pick your ice cream. And your friend goes up and they pick their ice cream. Well, just because you picked cookies and cream doesn't mean that they can't also pick cookies and cream. They have the same choices that you had for your choices. So when our subsequent events have the same choices, those same totals of possibilities, then we have an independent event. Now, if I show up to class and I have 3 different candy bars, and I have a Snickers and a Twix and a Reese's, and my first student comes up and they choose a Snickers. Now, my second student can only choose from a Twix or a Reese's. These are called dependent events because the second person has a limited set of choices depending upon whatever the first person chose. So dependent events always limit the choices. You're going to have a smaller set of choices that are following. It's going to narrow down your options. So that's a good way to think about it. If you are narrowing down your options, you have a dependent event. So first, let's address independent events. So similar to as we dealt with mutually exclusive in 12.4, when we have a dependent event and we are using the word and. So we have event number 1, we call it A. Event number 2, we'll call it B. And we want both of them to happen. We want to be able to say yes to both of them. That's different than we're saying or. For or, it was either A or B. It didn't matter which one. Now, we are requiring that we have a yes to both A and B, whereas or uses addition and will always use multiplication. So we can break apart our probabilities in the same way that we did with the or, and we can say that if I have the probability of an event A and event B, I'm going to write it like this, probability of A and B, okay? So they're both happening, and neither A nor B have any effect on each other. So I have the same choices for A that I have for B. Then we can say that the probability of A times the probability of B will give me the answer to that question. So just as we did with or, and it was a simple addition sign, now when we have an and, it's just simply a multiplication sign. So if we are spinning a wheel and the wheel has 8 different spaces on it, and they're numbered 1 to 8. And I want to say the probability of spinning a 2 and a 3, if I have 2 different spins, I would say the probability of spinning a 2 is 1 out of 8. And so that's multiplication. The probability of spinning a 3 is 1 out of 8. So I have 2 different events. This is event 1 is followed by event 2. This one happens first, the second one, but they had the same total because when I spin the wheel, I didn't take a slice off. Now, if we want to look at dependent events, a good example is, say we have this wheel and we call it a like a wheel where you can take a prize off of it. And so I spin and I get a 2, and now I take off that prize. Now, when you come along and spin the wheel, you no longer have 8 prizes. So I had 8 out of 8 options for my event. I could have won any 8 out of the total 8. But now, when you spin the wheel, you only have 7 options to choose from. So these are dependent events. You can only have 7 out of 7 different choices there. If you would pick 1, I'm going to get 1 out of the 8. You're going to get 1 out of the 7 that are there. We've got a dependent event. So think about whether or not the event, what happens first, has an effect on what happens afterwards. Okay. Now, if the events do have an effect, then we call those dependent events, and we're going to write it a little differently. So if we have the probability of A and B, and they are dependent, we're going to say that we've got the probability of A, and now we're going to rewrite this back part. So we're not getting a new equation. We're just replacing this one. We're saying that we're multiplying with and the probability of B given A has already happened. So we say this, or it is written as given or depends on. Now, the tricky part, or the part that can be tricky, is that when we go to event 2, remember this is event 2, we are automatically assuming that event 1 had a positive outcome for whatever it wanted to be. So if we are drawing cards and we are saying the probability of drawing a red and then the probability of drawing a 10, given that you drew a red, we are automatically assuming that we 100% did draw a red, that we answered this with a yes, that it was true, that it was positive. So that helps us make the logical steps of, if I'm looking for drawing a 10, given that I drew a red, well, I could have drawn a red 10 also. So that would be a part of it. So we always need to address our second event in light that the very first event happened as a positive outcome for what we had. So those are the 2 main takeaways for 12.5. The probability of an independent event, which is simply multiplying them together. The probability of a dependent event, which means we multiply them together, but we understand that that second probability will always have less options initially. So if you find that your numbers, say we're looking at 1 out of 52 for our first event, and we know that they are dependent, and you have the same numbers on the bottom. So you have the same options, 52 options for the first one and 52 options for the second one. This cannot be a dependent event. A dependent event will always have a limited option based upon the first one. So when they are the same, that's a good check. If you put the same number and they told you that it's dependent, then we've set up our problem wrong in the first place. Okay. We learned this in 12.1 and 12.2 with the fundamental counting, whenever we said something can be done with a duplicate or without a duplicate. So if we were looking at doing a license plate, and we have letters for the first one, and we have numbers over here for the second part, we said if we could duplicate, we would have 26, 26, 26. Those would be independent events. It doesn't matter what you pick on the first one. If it was dependent, then we had 26, 25, and 24. Because once I picked this first letter, it's out of the drawing. We're not allowed to use it anymore. So my second letter now depends upon whatever I picked on my first one. So let's address a couple of the homework problems. For 12 through 17, it says you're spinning a wheel. So let's think about it. If I'm spinning a wheel, every single spin is exactly the same. It doesn't matter what I spun on the first time. It doesn't weight the wheel differently. It doesn't give me a different chance. So spinning a wheel is all going to be independent events. We are simply going to be multiplying the probability of your first one and times the probability of the second one. And that one requires you just to know how many total slices of the wheel that you have, how many pieces, and then how many colors, how many of those slices are each color for the wheel. Okay, so let's address 18 through 23. It says find the probability of drawing the given cards from a standard 52 deck of cards. So again, we're back to our deck of cards. We've got 52 total in here, 4 suits, 13 cards per suit in each one. And the A portion says with replacement. So that means I'm going to take maybe one card out, and then I'm going to put it back. So my event 1 means I'm drawing from a deck of 52 cards. And then for event 2, I put the card back, and then I draw again. So when I put the card back and it said with replacement, that means we started back over. So these are independent events. And I also have 52 options for the second time that I draw. Now, if for part B, when they say, now also find the probability of these without replacement. So let's address number 18. The probability of drawing a heart and then a diamond. So a heart and a diamond. So we're going to look at it, and then we rewrite this as my first event number 1 is the probability of drawing a heart. My second event is probability of drawing a diamond given, so we drew the line, given I already drew a heart. Okay? And those are multiplied because we are saying and. So the probability of drawing a heart, so I have 52 cards. What are my chances of getting a heart out of there? Well, I've got 13 cards that are hearts out of 52 cards. Now, for event 2, we have to assume that we 100% did draw a heart. Okay? So how many cards do we have left? So we drew our heart card over here. So now I only have 51 cards that are left in that deck. Then we have to ask our question. Now I want to draw a diamond. Did drawing this heart card have any effect on how many diamonds I have left? No, it did not, because I'm saying that 100% I drew a heart. So there are still 13 diamonds left in this set. So there are 13 diamonds left, but there are only 51 cards left. So our probability of drawing a heart and then a diamond is adjusted because instead of having 52 and 52, we had 52 cards in the first draw, but we only have 51 cards in the second draw. Okay. Let's look at number 22 since there are 3 of them involved. We can do this for as many as we want. It says the probability of drawing an ace and then the probability of drawing a 2 given that you drew an ace. And then the probability of drawing a 3 given that you drew an ace and a 2. Okay. So if we were looking with replacement, all of these are independent events. So the probability of drawing an ace is 13, or sorry, there's 4 aces. So we have 4 aces out of 52 cards. If I looked at 2s, I have 4 2s out of 52 cards because I put it back and I start back again with 52 cards. The probability of drawing a 3, there's 4 3s, and I put all the cards back again. So I still am starting with 52 cards. So with replacement, we have equal bottom numbers because we've put them back. We're starting with the same amount each time. But let's look at it if we were doing without replacement. So we say for an ace, well, I have 4 chances in a whole deck of 52 cards. So now I actually have this ace sitting over here. So how many cards do I have to draw from now? I only have 51 cards to draw from because I have one that was taken out. So how many 2s do I have? Did drawing this ace take out a 2? No. So there's still a chance. There's still 4 2s sitting in that pile. So now I have a 2 sitting out. So now I'm going to draw again. How many cards are in my pile? So I have this big pile over here, but I've pulled some out. How many cards? I now only have 50 cards, and I want a 3. Have I gotten rid of a 3? No, I got rid of an ace, and I got rid of 2. So these 2 cards have no effect on how many 3s I have. I still have 4 3s as an option from that. So that's how we would set up our probability without replacement for more than one event. There. Let's see. Okay. For 33, it says you and 4 friends, so we're looking at 5 people, okay, go into the same store at different times to buy costumes for a costume party. It says there are 20 different costumes. So hanging up on a rack, you have 20 different costumes, okay? And the store has at least 5 duplicates. So there's 5 of this one, 5 of this one. There's 5 of all of these. So there's enough where you could all pick the exact same costume. You taking a costume out of the store does not get rid of that option. Okay, so that's the main thing. Now, if they said they have 20 different costumes, and there's only 1 of each costume, that means when your first friend walks in and they pick a costume, that option is no longer available to you. And then the second friend walks in and he picks a costume, that costume's no longer available. So by the time you get down to the 5th friend, there are 4 different options that are no longer available to him. So the thing that they are saying whenever they give us that statement that says they have at least 5 duplicates of each costume, they are giving us information that this can be worked as an independent event. Because if you pick a costume, there's another one to fill its gap. So your friend, when they come in, they also have the option of choosing that costume. So it says, find the probability that all 5 that all 5 choose different costumes. Okay. Now, this one is one of those ones where we look at and we go, do I really want to find that? So if all 5 choose different costumes, that means that no one chose the same costume. Okay, so how many ways could you choose it? I think we can work it out like this. So first we need to have the total ways that 5 of you could choose the costumes, right? Now, because these are different costumes, we've got a permutation problem here because the order would matter. If you're dressed as Spider-Man and your friend is dressed as Batman, that's different than if you're dressed as Batman and your friend is dressed as Spider-Man. So if I had 5 friends, we could write this 2 different ways. I've got 5 friends and I have 20 options, and my friend walks in, he's got 20 options, third 20, fourth 20, fifth 20 different options. Then we've got 20 to the 5 different ways that we could get a costume. Okay. Now, how many ways could we get a different costume? Okay. So we're wanting everybody to have not the same costume, which means that my first friend picks a costume and the second friend doesn't pick that one. So he only has 19 options to choose from. Then third friend can't choose either one that he picked. So that'd be 18, then 17, and then 16 on it. So this is how many ways that we could all pick different costumes divided by the total number of ways that we actually could have the same costume. Okay. And so when we work out those numbers, I'm going to switch back over here and see. We can see that our first friend, I kind of broke it out. Our first friend picked a costume. He had 20 out of 20 costumes he could pick from. Our second friend had 19 out of 20 costumes to pick from, 18. And what we got was 20 times 19 times 18 times 17 times 16 for the top, and 20 to the 5th for the bottom, which gives us 0.581 for that.